So we left it at the expectation values I was checking now. So expectation value formula. Basically, what I'm trying to understand, right? So quantum mechanics. It's really from. I'm just trying to understand why the formula makes intuitively sense. Okay, because from a purely position perspective, common integral expression, expectation value may then be stated like this. General formulation. Because the expectation value is in the end some sort of average, right? Expectation value. Operational definition. Consider operator A, the expectation value of the operator, right? So the thing is, it's telling you it's a property. It's a property of the operator. The operator being the thing that you're doing, sort of the thing you're measuring, right? So if you're measuring the observable, I'm measuring position. Then you have the position operator. Indirect notation. In quantum theory, an experimental setup is described by the observable A to be measured, and the state of the system, the expectation value of A, in this specific state is denoted like this. Mathematically, A is a self-adjoint operator in the Hilbert space, pure state, and then this is a formula for that. If dynamics is considered, either the vector psi or the operator A is taken to be time dependent, depending on whether stronger the picture and which is used. The evolution of the expectation value does not depend on this choice, however. If A has a complete set of eigenvectors with certain eigenvalues, then the expectation value turns out to be the sum of these eigenvalues. Okay. This expression is similar to the arithmetic mean, exactly. So illustrates the physical meaning of the mathematical formalism. The eigenvalues are possible outcomes of the experiment, and their corresponding coefficient is the probability that this outcome will occur. It is often called the transition probability. The probability simple case arises when A is a projection. A particular simple case arises when A is a projection. But let's dive more into the why does this work, right? Or even the in the continuous spectrum. So in quantum theory, it's possible to operator have a non-discrete spectrum, such as the position operator. This operator has completely continuous spectrum with eigenvalues, eigenvectors depending on the continuous parameter x. Specifically, the operator x acts on a spatial vector. In this case, the vector psi can be written as a complex valued function on the spectrum of x, usually the real line. This is formally achieved by projecting the state vector onto the eigenvalues of the operator. As in the discrete case, it happens that the eigenvectors of the position operator from a complete basis obey a closure relation. The above may also used to derive the common integral expression of the expected value. So that's the integral expression. By inserting identities into the vector expression, then expanding in the position basis. So this is specifically, this is what I was looking at before, right? So two things to basically unpack here, right? So why is the transpose used in this context, mathematically speaking? Where the basis vector to a single integral. To the composition in quantum mechanical integrals. All the above formulas are valid for pure states. Only. Interesting. Prominently in thermodynamics and quantum optics, also mixed states are of importance. These are described by a positive trace class operator. The statistical operator or density matrix expectation value can then be obtained. Okay. Okay, so what is this here? So what is the example in configuration space? As an example, consider a quantum mechanical particle in one spatial dimension in the configuration space. In classical define the configuration of a system, or called generalized configuration space of a physical system. Okay. Here, the Hilbert space, the space of square integral functions on the real line, vectors, functions, called wave functions. The scalar product is given by this. The wave functions have a direct interpretation as probability distribution. Okay, so you're doing that because essentially that's how you calculate the probability distribution. Okay, it could be that's as simple as that. It's a probability of finding the particle in an infinitesimal interval of length. As an observer, consider the position operator Q, which acts on wave functions. These. Okay, the expectation value or mean value of measurements of Q performed on a very large number of identical independent systems will be given by these. So, yeah, okay. Now this makes sense. Now, the reason we're doing the product like that is because we want to calculate the probability density. It's the sum of all the different probability densities. I think that's a nice, and then the probability of each x. I would say that's kind of that's kind of how I would read this. That really makes it look like an average, right? In average, you'll find it there. Like there's 50% chances of finding it here, 50% chances of finding it there, so you'll find it like in the middle. That will be the expectation value. I'm not so sure although from a sequential perspective, that's a bit odd, right? It's like you have the state, then you apply the operator, and then you... So you evolve the state. It's not that you're evolving it, it's that you're... This is easier to understand than the Dirac one, right? Because this is the wave function. Then you have the operator. So you're applying the operator, you're making the measurement, and then you're multiplying by the Uh, the transpose. The expectation value on existing operation is not the case for all vectors because the position is unbounded and has to be chosen from its domain of definition. Calculate the average momentum when it's the momentum operator and configuration space. Okay. Okay. Viral theorem. Since discrete particles bound to potential forces. In mechanics, the viral theorem provides a general equation that relates the average over time of the total kinetic energy of a stable system bound by potential forces, that of the total potential energy. Okay. So still, I'm not so sure I understand I understand fully how to read the result of I have an operator and I apply the wave function, and what does this tell me or give me, right? Like, because if I have a wave function and then I multiply by x, like, what does this tell me? You know what I mean? That's definitely it's kind of in a way here. It's like you're applying an operator, but you're not like applying an observable. Applying an observable is because an observable is a special kind of operator that probably then actually does this projection. Um, Not entirely. This makes sense. Okay, so there's an explanation for this, which is you want to calculate the probability. It's like the sum of like an average, right? So you're integrating over, and then it's the operator times the probability. Still not so sure. I don't feel 100% comfortable with this. I understand. Yeah, I understand the expression, but it's like, no, yeah, that's the point. It's an integral, right? So you're doing this for every single point, for every single dx. It's a sum of every single dx. That's what you're doing. So yeah, essentially that's what the expression means. Here, though, it's a bit trickier because, as I said, I would typically read these right to left, and I would say, boom, then we apply an observable. And why do we need to do this? What's like what's the maybe the next thing to check. I'll leave it here for now, and we'll do another session later, another brief session later. But this makes more sense. I'm not so sure why X makes sense though, or in a way, why is the operator? Shouldn't these really be? Oh no, these should be the eigenvalues. That's true. These are the eigenvalues. It's not the operator. That's true. Right? These are the eigenvalues, correct? It's formally achieved by projecting the state vector onto the eigenvalues of the operator. As in the discrete case, is the projection. It happens that the eigenvectors of the position operator form a complete basis. There you go. If A has a complete set of eigenvectors and eigenvalues, and that's what you're doing, these are the eigenvalues. And I think that's, and then in that case, X is also the eigenvalue. This is also the eigenvalues of the moment of the position operator, I guess. It's just X, right? I think so. To each observer in quantum mechanics, there's an operator corresponding to it. I don't understand what's the meaning of the eigenvalues of the X operator, since X is Hermitian and X correspond to real numbers, exactly. So, values that are measured in the experiment. Values are values of the position obtained when measured. Every measurement will produce a different result. Yeah. We're unwrapping some of this stuff. We're moving a little forward, step at a time. We're unwrapping some of this stuff just to feeling more comfortable with this notation, with notation and elements and stuff like these.